If we're live, the wheel. Okay, here we go. Welcome everyone to our nodes talk. Today, if you've been before, you know these presentations are brought to you by the University of Manitoba Data Science Nexus. Before I say anything else, we want to acknowledge that the University of Manitoba campuses are located on original lands of Anishinaabeg, Cree, Oji-Cree, Dakota, and Dan peoples, and on the homeland of the Métis Nation. We respect the treaties that were made on these territories. We acknowledge the harms and mistakes of the past. We dedicate ourselves to move forward in partnership with Indigenous communities in spirit of reconciliation and collaboration. So if you haven't heard of Data Science Nexus, I'll just tell you a little bit about it. It's an interdisciplinary collaboration center at the U of M, housed in the Faculty of Science. And the aim of these talks, is to demonstrate the many current and existing research areas of data science and associated applications. So if you've been to our talks, we've had many speakers in a variety of areas and fields. And we thank you for joining us and hope you can continue to join us in the future. As you know, the talks are live streamed on YouTube, and during the talk, there'll be a Slido code. I'll put that on the screen. Today's code is 99248, so you can put questions in there. And at the end of the talk, which will be about 45 minutes, I'll pose those questions to our speaker. So I'm very pleased to introduce our speaker. It's Dr. Stephen Pistorius. Stephen is a professor and associate head, medical physics and physics and astronomy, professor in radiology and anatomy and cell science here at the U of M. He also serves as the Vice Director and Graduate Chair of the Biomedical Engineering Program and is Senior Scientist at the Research Institute in Oncology and Hematology. Some more about Stephen, some of his background. He holds a BSc in Physics and Geography from the University of, I don't know how to say that, Natal KwaZulu. Okay. And an honors Bachelor of Science in Radiation Physics, a Master of Science in Medical Science, and a PhD in Physics from the University of Stellenbosch in South Africa, and a postgraduate diploma in Business Management from the Edinburgh Business School in the UK. He has had several work experiences in industry, and in particular, I want to mention that he worked for more than 2 decades as an active researcher at Cancer Care Manitoba, even acting as the Provincial Director of Medical Physics from 1995 to 2010. His research interests focus on image processing and reconstruction, medical device development, improving, optimizing, and quantifying various diagnostic and therapeutic techniques, and in modeling and understanding radiation transport and clinically useful imaging and treatment modalities, and particularly as they apply to more equitable healthcare to persons in disadvantaged communities. He has many publications appearing in high-quality journals such as Medical Physics, IEEE Transactions on Biomedical Engineering, and IEEE Transactions on Image Processing, to name a few. He is supported by an excellent and diverse group of graduate and undergraduate students who make his work possible. So he's a very active researcher, and I'm very happy he accepted my invitation. And I'm happy now to turn things over to Stephen. Thank you.
Thank you very much indeed for the kind introduction. It's nice to be here. Hello to everybody. Today, I'm going to be talking about advanced image reconstruction and machine learning in positron emission tomography and microwave imaging. And at the outset, I would like to thank both the authors on this paper as well as the many other graduate and undergraduate students who've helped me over the years in this research, without whom this work would not have been possible. And so here's an image of some of those students taken pre-COVID summer in 2019. So I'll take us through a series of steps, first introducing breast microwave imaging and sensing, before talking a little bit about some of our research progress in this field, before then moving on to scatter imaging associated with CT and positron emission tomography and some of the research progress there, before wrapping up with conclusions and future plans. So one of the challenges that faces us with breast cancer particularly, which is going to be the focus of the first part of this talk, is that it's the most commonly diagnosed cancer in most of our developed countries, with about 25% of the cancer incidence in Manitoba being associated with breast cancer. As you can see from this the slide, the dark blue sections are the regions where we have high breast cancer incidence, and it shows up in Northern America and Europe, Australia as the highest regions. The challenge that we face, though, is that in spite of this, we find that almost 50% of our breast cancer cases and almost 60% of deaths associated with breast cancer occur in the less developed countries, as showing the mortality in this map, where we can see the dark red tends to focus very much in Africa. And as these less developed countries and rural communities start to adopt more westernized lifestyles, we're going to start to see the incidence increase. And unless we're able to manage the mortality, we're going to see a huge healthcare crisis evolve over the next couple of years. Mammography, particularly X-ray-based mammography, is known as the gold standard. But unfortunately, it's relatively costly and is only feasible in regions where there are good health infrastructure, such as in Europe and Northern America. And it's a bit of a challenge in places like Africa to have good screening programs in place. And at the end of the day, the priority really should be for these low and middle income countries to try to find ways of improving its early detection. And these have their own cultural, economic, and political barriers, which we have to overcome. So our aim is to improve access to breast cancer screening, particularly for disadvantaged communities in Canada and worldwide. And we're going to be doing this by developing a portable and low-cost device that is suited to the needs of these communities, and that places ultimately healthcare in the hands of women so that breast cancer can be detected as early as possible, treated, and thereby save lives. Now, our current commercial technologies that are used right now for breast cancer detection include mammography, which is the key one, but magnetic resonance imaging and ultrasound also play a role. While X-ray mammography is the current standard, it's not the perfect screening method. Some of the challenges that we face are that it uses ionizing radiation, which in itself can cause cancer. It has a relatively large false positive rate, which is something we would like to try to reduce. It needs breast compression, which for many women is uncomfortable. It needs, as I mentioned earlier, good human and capital infrastructure to allow us to develop good screening programs. And for dense breasts, which occur particularly in younger women, it's not ideal. The image on the right shows a typical mammogram of a breast, showing the regions that we're particularly interested in. There's a region of fatty or adipose tissue, a region of denser fibroglandular tissue. And it's our goal to try to find the tumor present in this relatively complex structure. Now, as I've said earlier, the current imaging techniques, whether they be mammography, MRI, or ultrasound, don't really meet our global health requirements. And the benefits of the microwave imaging and sensing modality is that it's non-ionizing, so it's safer and permits frequent examinations. It tends to be more sensitive inherently to tissue contrast than we see with mammography. It uses no power. In our case, in our hands, it uses less power than that of a cell phone. And it's relatively inexpensive in comparison to X-ray and certainly to MRI. And finally, it can be quick and comfortable because we don't require breast compression. So our goal is to try to complement the current technologies with this new device. And the current techniques are mammography, as I said, MRI and ultrasound. And while we certainly see high sensitivities with MRI, its comfort and cost are somewhat of a challenge. Ultrasound is also a low-cost device, but requires good infrastructure to be able to be used. And so microwave sensing hopefully will give us a device which is comfortable, relatively low cost, high availability, and reasonable sensitivity, at least the sensitivity of a traditional X-ray mammography. Now, how does this work? Well, we have a breast microwave imaging system that illuminates the breast with a microwave signal coming from some form of antenna. And we measure the resultant scattered field that comes back from the breast. And we have to analyze this data to try to detect the presence of the unwanted malignancy. The contrast that we're seeing is effectively caused by the different dielectric properties of the malignant and healthy tissues. And so here again is a breast outline, basically a breast phantom. We have the adipose or fatty tissue on the outside. We have the denser fibroglandular tissue and the tumor, which we're trying to detect. And so at the end of the day, this is the region that's going to be scattering more than the surrounding regions, and we're trying to detect that increased scatter. Now, there are a number of challenges that face microwave imaging. The first is, how do we go about coupling the microwave power into the tissue? And the tissue is made up of a number of different materials with different dielectric properties, but the skin has the big challenge that there's a huge differential between that of air and the skin layer, causing significant reflections. Now, many systems immerse the breast in a coupling medium, but we've elected to do this in air for a number of practical reasons. But this does lead to a challenge in terms of trying to get the microwave signal into the tissue in the first place. If we can't get it into the tissue, we're going to be unable to detect the presence of the tumor. Once we get the signal into the tissue, we have to be aware that there's a variety of losses that take place in terms of this signal attenuation, which drops off as a function of distance and with increasing frequency. We also need to try to find a way of increasing the resolution of the system. In radar-based systems, we need to be able to increase the bandwidth and have a large number of scan positions. And finally, we need to try to find ways of increasing the gain and reducing the size of the antenna. These challenges are somewhat difficult because the higher the frequency, as I said earlier, the smaller the penetration depth, but the lower the frequency, the larger the antenna size. And so these play off against one another. Finally, we have to look at trying to find ways of optimizing our reconstruction and sensing algorithms to improve the resolution, to give us early detection, try to find ways of getting good contrast or sensitivity to help reduce the number of false negatives that we detect, and trying to increase the specificity to reduce the number of false positives. And this is where I'm going to focus the work today. So most of our research has been done using a Health Canada licensed Class 3 medical device, which we have developed. And we'll be using this device, which consists of a rotating platform onto which our antennas are mounted. This is a stage that can be raised and lowered as the system rotates around the breast, which is pendant through a hole in the bed here. And this is a view from the top. We have a system onto which these antennas are mounted, and so we can have one or more antennas around the breast collecting data at the same time. And this information is then fed to a system which reconstructs the image. And we'll talk more about that in a moment. And we're also developing a prototype portable system, which we will, in the coming months, be evaluating and collecting additional data from our various phantoms. And this system is a little different in that it has no rotating parts. It's designed to be much lighter and obviously portable, running off battery power. It's made up of a number of antennas, potentially in 2 layers, collecting data from the breast and feeding those into individual nano VNAs, which stands for Vector Network Analyzer. And these VNAs are in turn going to analyze the data and feed that back to the computer. There will, if necessary, be amplifiers to enhance the signal response from these antennas, which are placed on the surface of this ring, with the breast being pendant into this opening. Now, to enable us to analyze and evaluate these systems, we've made a lot of use of phantoms, which provide us realistic models for testing. And to get these, we've taken MRI data of breasts, and we've converted that data into a 3D model for printing, as is shown in this slide. So if we have our original MRI data shown here, this has been processed by using various blurring functions to allow us to create a CAD model of the prototype, which is then 3D printed in 2 components, an outer adipose shell, which will hold a liquid which mimics that of adipose or fatty breast tissue, and an internal fibroglandular shell, which again holds a liquid which mimics that of the denser fibroglandular tissue. And these are placed inside one another, and into these then is placed a tumor as well. So let's move on to the actual research that we've been doing. So the 2 systems that we use operate over different frequency ranges. The bed system operates over a frequency range of 1 to 8 gigahertz, while our portable system is designed to operate over a range of around 0.7 to 3.5 gigahertz. And the data is converted from this frequency domain to the time domain. And we create what we call a sinogram, which is then used to create our image here using various image reconstruction algorithms. And then this image is then used for diagnosis. So we'll have an expert who will actually read this image. How do we go about doing the conversion from the frequency to the time domain? Well, we use either the inverse Fourier transform, or in our hands, the inverse Chirp-Z transform, which is used for this conversion because it allows us to get superior time resolution, as is shown in this series of images here, where we can see if we have a relatively long time step size, the ability to resolve the tumor is very poor. As the time step size gets shorter, we are able to resolve the presence of this lesion standing out against the background clutter and noise in a much better manner. The sinogram is effectively a map in the time domain of the response from the tumor as a function of the scan position and where the antenna is in its rotation around the breast, and as a function of the time response, or effectively the depth at which this occurs in the breast. This being nearest to the antenna, and so reflections, at the point here will be closer to the antenna than reflections from further down within the breast structure. And we will analyze this data to allow us to extract the necessary information to give us an image. The process that we typically have been using is a system which uses the basis of a maximum likelihood expectation maximization algorithm, which has been derived from positron emission tomography approaches and has been adapted for breast microwave imaging. And the way it works is we'll take an initial estimate of our object, and this could be simply, in the case of a breast, just a simple circle for a cross-section through the breast. That's then forward projected into that estimate is then forward projected into the time domain, and we compare this result with the actual measurement. And so this would be an actual sinogram, for example, or this would be our first forward projection. These are then compared, and then that difference is back projected into the object space to give us an updated estimate. And so this process is repeated until we obtain a good image quality result. Now, in a radar model, the radar model is what we use as our forward projection. And we use what is called the delay and sum model, which is a very traditional beamformer as our update back projection approach. And so we'll use this as an iterative fashion, slowly building up the image quality. Now, the one advantage of this iterative approach over the standard delay and sum model is that it allows us to build in a variety of different corrections for things such as the antenna beam pattern, the output pulse shape for multiple scatter, or for material-dependent propagation speed, for example. And so this would be implemented here before we obtain the final image. And I'll just give you an example of that. Well, firstly, let's look at the iterative algorithm versus the delay and sum algorithm. A delay and sum reconstruction would give us an image that looks something of this nature, where it's somewhat difficult to see the presence of the lesion against this background clutter. We have a relatively poor signal to maximum ratio and poor signal to clutter ratio, as is shown here, in comparison to this iterative approach here, where the tumor stands out quite clearly against the background with a much better signal to maximum ratio and signal to clutter ratio response. Here is an example of the modeling of the pulse. And so we've modeled the time domain pulse with a full Gaussian with a full width at half maximum, which matches the pulse reasonably well. And this is then applied again as a correction. And here again, you can see a somewhat smaller but still significant improvement in the image quality here between an uncorrected image with a signal to maximum ratio of 30 dB in comparison to the one on the right, where we have done a time pulse corrected image and we get a somewhat larger signal to maximum ratio of 36 dB. These are 3 centimeter tumors in relatively fatty breasts. Now, one of the other benefits we bring to the research is that we have probably we believe the largest imaging data set available in the world as a result of these phantoms that have been developed. And so we have a series of adipose and fibroglandular shells of various different shapes and sizes that can be used to represent breasts of different densities. And so here's an example of some of them. We have two series of these shells. And so by mixing and matching various fibroglandular inserts with the adipose shells, we're able to mimic breasts not only of different sizes, but as I said, also of different densities. And these are our two generation of phantoms that we have developed to give us this relatively diverse and representative set. Our first number of phantoms could give us 13 unique combinations of breasts. This next generation that we developed could give us 66 unique combinations of breasts. They use slightly different materials for the 3D printing process. We could have more variability in the positioning of the fibroglandular shells within the breast in the new generation phantoms. And this also provided us with greater tumor positioning. And so this has allowed us to create many, many more breast tumor combinations than we could previously. And so what we do is we take our data collected here, we turn it into our sinograms, and we carry out this image reconstruction algorithm to obtain the diagnosis. But to do that, we have, again, a couple of challenges that we face. We not only need this good image reconstruction algorithm, we also need to find a way to suppress the responses from the skin, which can otherwise overshadow the responses from the tumor, particularly if that tumor is superficial. We need to find ways of determining a detection criteria to identify whether a tumor is present or not. And this is an example of what happens with the response from the skin surface. Here, this is a sinogram. If it's reconstructed using a standard delay, multiply, and sum algorithm, we're likely to see a strong response from the breast surface. And we need to find ways of trying to suppress this if at all possible. Now, we have looked at various analytical skin suppression techniques, including the use of singular value decomposition, but none has proven to be particularly robust. And what we'd ideally like to go is from something that looks like this image on the left, where there's no skin suppression, to something that looks something like this on the right, where we have skin suppression, allowing the effects of the tumor or the response to the tumor to show up quite clearly on the right image, whereas it's hidden on the left image. And one of the things that we've identified is that the pixel locality in the sinograms has yet to be widely exploited. And so we felt that convolutional neural networks, or CNNs, could potentially be utilized to exploit this locality in our sinogram data. To do the skin suppression, one of the things we have tried is to generate a large number of simulated geometries, for simple breast models, to create simple sinograms, which were created to allow us to do a series of transfer learning cases, or develop a number of cases for transfer learning. And these were used then within a standard CNN network to try to obtain skin suppression, as is shown here, where the input was fed into a variety of convolutional max pooling layers, dense layers, reshaping, and finally flattening layers before giving an output. And the last convolutional layer was used as the trainable layer following the transfer learning training of the earlier stages. And fortunately, while we get reasonable results, and this image shows the gold standard response for a 3 centimeter tumor in one of our phantom geometries, this network was only able to generate the tumor response with an accuracy of about 3.5 millimeters in terms of its position, and with unfortunately very low specificity. And so this has led us to try to investigate alternative operator-free or image-free detection approaches. And this is where we'll now take our sinograms, and rather than creating an image we'll just go straight to the diagnostics perspective and output the presence or absence of a tumor. How is this done? Well, again, we'll take our data. We typically subtract an empty chamber scan to allow us to calibrate the system. From that, we collect our complex frequency domain information, which is ultimately then turned into a time domain data set, and we'll make use of a window within this data set for our training of our system. Obviously, we have to go through a number of steps, including pre-processing and augmentation of our data. We need significantly more data to train than we get out of our standard data set, in spite of its relatively large size. And we do this by doing reflections and translations on our sinograms to increase the size of our data set quite significantly. Numerous different architectures have been implemented, and our performance has been evaluated using our Phantom test set. Again, typically we'll take our input, we'll feed it into a variety of convolutional layers, max pooling layers, dense layers, before predicting whether there's a tumor present or absent in our data. On our very first attempts with this, and on our Generation 1 data set, we got performance metrics which were extremely encouraging, maybe too much so, but they certainly showed that this approach, using convolutional neural networks, gave us results which were very comparable to that of digital mammography. Both in terms of the area under the curve of the receiver operator curve, the diagnostic accuracy, the sensitivity, and the specificity. We've gone on to look at this in some greater detail, and using all of our data, we've done a trained test set variance, which was maximized by testing on unseen adipose shells. And this was aimed to try to evaluate the true generalizability of our classifiers. And so we would take a certain number of adipose shells, we would train them, we would then use that trained model to test a shell which had not been seen by the training system, and we were able to report the results on that. And this final slide here shows our CNN performance on unseen phantoms. And so this is where these phantoms have not been seen as part of the original training. And you can see that provided we don't include the smallest and largest phantom sizes, which were the A1, these are very small. The A3 was the largest phantom. We get relatively good performance measured by the area under the curve of the receiver operator curve. So moving on then, I would like to talk about scatter outside of microwave imaging. Although we have a significant amount of scatter in microwave imaging, we also have scatter in other areas of imaging. And this is particularly true in CT and in positron emission tomography. And our traditional assumption in the imaging field has been that scattered photons are noise, and we should try to remove them in whatever way we can. The question that we've really posed is, how do we go about harnessing the scattered radiation to improve our image quality and to lower the dose, and ultimately to provide improved diagnostic and therapeutic benefits to our patients? And this is just an example, a Monte Carlo simulation showing the effects of scattering from a beam coming into a typical physicist's phantom, a cube here, scattering in all different directions. And whether we could go about actually determining what was going on in this cube by measuring these scattered photons, in this particular case in two planes on either side of the cube. The challenges that we see both in CT and in breast CT are the fact that we have potentially large scatter levels. These scattered photons lead to an increased dose to our patient. And they also, the other challenge we have with CT in general is that we can't really characterize the tissue completely, because what we're measuring in CT is what's called the linear attenuation coefficient, which is a measure of the probability of an interaction in a particular tissue. But this interaction is a function of the atomic number and the electron density, as well as the energy of the incoming photons. And so it's difficult to extract this on its own from CT. In positron emission tomography, we have similar problems where the scattered photons increase our noise and degrade our image contrast. The other challenge we face in positron emission tomography is we're not only trying to identify the activity present in the patient, but to do that, we need to be able to correct for the attenuation of those photons before we detect them. And this is done quite often using either CT or MR scans. The challenge is that CT has a different energy to that of positron emission tomography, which makes use of 511 keV photons as a result of the positron electron annihilation. And so these have different mu values. And so how we convert from the one to the other is not clear cut. With magnetic resonance imaging, the challenge is even more so, is magnetic resonance imaging doesn't give us anything to do with mu. And so finding a way of converting that or estimating the mu from the MR is, again, not without its challenges. So how have we gone about doing this? Well, we started off very simply using a first-generation benchtop system and Monte Carlo simulation to try to estimate the scatter obtained in a simple system, using what we've tried to make as monochromatic as possible by filtering an X-ray source. And this rotated around the object, which was stationary in our particular case. Then using various modeling, we could show that the mu value shown here for particular tissues didn't entirely characterize everything, as I said earlier. And if we have electron density images, they will only show up if we have a technique that is able to extract the electron density images from the data we're collecting. And so shown here is one that just does a very simple correction or calculation to get the electron density, and another image here where we've been able to extract it making use of multiple scatter. And so this is the first sort of attempt to show that scatter in particular plays an important role, or can play an important role in us to be able to characterize the tissue to a greater degree. This shows, again, what happens if we have no correction, where the errors between the actual and the real are quite large. As we increase the correction that we're making use of for attenuation, so the error images start to approach zero. And for a somewhat more realistic breast phantom here, which contained a number of different types of tissue, again, we could show that using scattered photons, we were able to more accurately calculate these different tissue types within the breast. And then again, even a more realistic breast phantom, where we had adipose and glandular tissue or fibroglandular tissue and blends of 50-50 of both of these, and ultimately the mean error for a correction which took into account both position or length and the correct attenuation coefficient gave us errors of less than or better than 1%. Now, the challenge with these early approaches is that they used scanned pencil beams, which are time-consuming, and so we started to move towards a more realistic approach, which uses what we call a spectroscopic Compton scattering mechanism, which measured both the position and the energy of those scattered photons, using ideally flat panel detectors. I'm not going to spend any time on this equation, except to say that we make use of an equation which describes the number of scattered photons using Compton scattering, and the Compton scattering relationship between the energy of the scattered photon and the energy of the incident photon has this angular component in it. And so by measuring the position and the energy of that scattered photon, I can determine that that photon scattered somewhere from this inscribed arc shown here. And so unlike traditional CT and positron emission tomography, where the reconstructions are done along straight lines, our work typically uses reconstructions along curved arcs. Now, the nice thing about this approach is that it gives us some additional benefits. And because we're now detecting both energy and position rather than just position, we can get away without as many positions of rotation around the patient as we would typically need. And this is a reconstruction shown here with a single projection, where I have what's called a C sinogram, which is a more complicated form of the sinogram which I showed earlier, which now is actually three-dimensional. It has detector positions, scattering energy. And then the third dimension, which is not shown here, would have been its rotation around the patient. And the challenge that we're going to face, and we do face, of course, is that this requires us to have good energy resolution, as is shown in this image here, where as we increase the energy resolution of our detector from 1,000 electron volts down to 100 electron volts, you can see the quality of the reconstructed image improves. However, as I said earlier, one of the benefits is that while conventional CT requires a large number of projections to give us a good image quality, the number of projections plays a smaller role in scatter CT, and by even 8 projections, we're getting a reasonable quality image, whereas with 8 projections with CT, we see nothing at all. So where have we gone with PET with this? Well, we've looked at evaluating the feasibility of using scattered photons to enhance our PET imaging systems, to improve the image quality and or reduce the dose, and to provide the anatomical information and or attenuation corrections that the electron densities give to us. Again, this uses similar equations to that I showed earlier, except now we're using and we're working at 511 keV, which is the energy of those annihilation photons that are being produced. Compton scattering is the predominant interaction modality here. And so on the image on the right-hand side, I would show a point here where the annihilation took place. This leads to the emission of 2 photons at 180 degrees to one another. Unfortunately, as given in this example, many of these photons will scatter through an angle, and this will lead to a false line of response because we're going to be detecting one of the photons here and one of the photons here in coincidence. And so traditional algorithms will assume then that the annihilation took place somewhere along this region here, whereas in fact it took place right over here. And so the question is, how do we go about determining this? So we use the same sort of approach that we used previously, and this again is a complex equation broken up into a number of smaller simplistic sections. We have to determine the photon flux at a particular point in space. We have to know the electron density at that point. We have to know the probability of a scattering event occurring at that point. We have to take into account the attenuation of the photons along the various paths that they travel. We have to consider the efficiency of detection of the detectors, and we have to look at various geometric cross-sections that play a role. And this allows us to estimate, if we know the energy of the scattered photon, again, like we saw with CT, to determine that the annihilation took place not along this path as it was in CT. Oh, sorry, apologies, I went too far. But at a point that lay between these 2 arcs. And so we created what was called a generalized scatter maximum likelihood maximization expectation algorithm, GSMLEM, that allowed us to determine both the activity distribution, which is applied within those 2 circular arcs, as well as the electron density map, which we can calculate along the 2D curve, much like we would have done with CT. The results are quite striking. What we see here is what we would get with purely true coincidences. So this is the ideal case where every photon is true. In other words, there's no scattering involved. This is what we would get if we just use the scattered photons using a conventional method. And while this image here is nowhere near as good as the image under A, or over A, it's the image that we would get by using the scattered photons using this approach. Now, it certainly is not as good as A, but it's certainly significantly better than B. And this set of figures shows how this improves as far as what we call the recovery coefficient. This is our ability to recover the contrast of the various regions that we're interested in against the amount of noise that's present. And the black line here shows the ideal case where there is no scatter present. And the red lines show what we get where we are able to use our approach to recover the contrast, showing an improvement, the ideal being to the top left-hand corner here, where we're able to recover the contrast perfectly with the least possible noise that we can. What happens is reverse. As we add scatter with the conventional techniques, things get worse, whereas in our case, as we add scatter, it actually gets better. The process is an iterative one. Again, we start off with some initial estimates. We update this in an iterative fashion, improving both the electron density reconstruction and the activity reconstruction in a stepwise fashion until we come back with a result here, which reflects both the activity uptake and the electron density distribution. Again, another example showing a reconstruction of a NEMA phantom with scattered photons and where they're mixed with both trues and scattered photons with a particular energy window that we can make use of. And again, here we can see relatively good ability for us to reconstruct the distribution of both hot and cold regions within this phantom. And another example showing again with a simple phantom and Monte Carlo simulated data with regions containing both hot and cold regions, how these various algorithms of ours, this is the standard line of response system. This would be our result with a full multiple scatter generalized type algorithm showing a much better agreement with the original phantom layout than we would see with the line of response. Now, one of the challenges that we face is that this approach requires excellent energy resolution detectors. And unfortunately, our current detectors don't meet this requirement. And so our hypothesis really is that convolutional neural networks have the potential to reconstruct our scatter images with the data that we're obtaining. And this hopefully will allow us to decrease our computational time, because one of the things I hadn't mentioned is that these algebraic iterative approaches can be very time consuming, and also improve our image quality by maximizing the useful scatter that we obtain from the scattered photons. We've done this in 2 steps using very simplistic analytical simulations of again, typical physicist style phantoms and more realistic 3D numerical phantoms obtained from patient data. And again, the approach is that we would take this data, we would create a radon transform and add noise to this to allow us to simulate these. The first set of data was trained using 100,000 training sets, again, using similar sort of CNN type approaches to what we've seen before. And then we can compare the reconstructed image that we obtained from this approach with the actual image. And what we have here is a comparison of the trues, the true reconstruction. On the left is the sinogram of this object. The results that we get from the convolutional neural network approach, that we obtain from the filtered back projection approach, which again is one of the standard reconstruction techniques in play. And we can see that the CNN approach does a very credible job with a relatively low error of being able to reconstruct these objects. Moving on to the more realistic situation, we had close to 300,000 sinogram pairs, which were used to train a DeepPET convolutional neural network. The sinogram was calculated using a PET simulator. And so a much more complicated arrangement, which took our PET sinogram and created an image from this data. We did this for cases where we were able to look at different energy windows. And so we have the trues, which are those photons which lie around the 511 keV photons that are emitted, as well as those that are associated with scatter. And those scattered photons will have lower energies. And so we've looked at different energy bins representing the photons which are detected with these energies. And so here again is a comparison between the trues on the left-hand side. On the right-hand side, we have the filtered back projection reconstruction, as well as an MLEM, a traditional MLEM approach to reconstruction. And then the 2 CNN approaches, one using 2D sinograms, and the other one using 3D sinograms, where what we mean by 3D here is that it makes use of the additional energies from the lower bins. And we can see, again, a relatively reasonable reconstruction of the true using the CNN approach. And if I look at a quantitative measure of that, this is looking at the structural similarity index between the true and our various different approaches, as well as the mean square error. We can see that in all cases, the 3D CNN performs better. So higher is better here, lower is better for the mean square error. So in conclusion, then, I'd like to say that what we've learned as far as our machine learning and microwave sensing is that it demonstrates improved area under the curve, potential better diagnostic accuracy and sensitivity with similar specificity to X-ray mammography. And our goals are really to develop and test a portable system and evaluate machine learning for this portable phantom data set, as well as to implement and evaluate machine learning methods that use both breasts for tumor prediction, and to develop improved reconstruction algorithms that consider multiple scatter and inhomogeneous propagation speed, and compare the classified performance, obviously, to the various image reconstruction techniques. And with respect to the PET scatter machine learning, we've again learned that the scatter algorithms are capable of improving the reconstruction of both activity and electron density distributions. The challenge being that the algebraic reconstructions are really sensitive to the energy detector, energy resolution, and that our early feasibility studies have shown that CNN reconstructions do have lower MSE and higher similarity than filtered back projection methods. And our goal here is to use Monte Carlo simulation and experimental data to train a CNN and use the entire energy spectrum, including the photo peak and scattered data, to generate activity and attenuation maps. With that, I thank you very much indeed for your attention. I'd like to thank the funding organizations that support our work and open the floor to any questions that you may have. Thank you very much.
Thank you, Stephen. That's a great talk. Thank you. There are some questions from the audience, so I'll just read these to you. So first we have, how far away is breast microwave imaging from being used in a hospital?
I hate that question, to be quite honest, because I always underestimate how long it's going to be before it gets used in a hospital or used clinically, because in fact we don't actually envisage this, at least not the portable system that we're focused on, ever being used in a hospital. Its goal is to be used outside of a hospital in much more rural clinical settings where it's not competing with the magnetic resonance imaging and ultrasounds and traditional X-ray mammography approaches, because it will never be able to compete with those. It is designed to be almost a pre-screening device to enable people who don't have access to those modalities to be able to detect the presence of a lesion quickly and easily, and then enable them to make the decision ultimately as to whether they can or are able to travel to a hospital for further follow-up and treatment. Now, I think I'm sort of getting around the question to some degree by answering like that, but my hope has always been a 5-year time frame. That's about as far into the future that I can see. We have had some safety trials on our bed system. I have exposed people in parts of rural Africa to the portable system and have had some good feedback from them, which has led us to developing a new prototype system, which will hopefully be better than our first prototype was. And I'm certainly hopeful that in the coming year or two, we'll be able to start doing some early clinical trials of those systems. As to when they'll become clinically in place, I really don't know, but I certainly hopefully it will be in the next 5 to 10 years.
Fair enough. That's a good answer. Under question number 2, what energy resolution do current PET CT detectors have, and what is needed for scatter reconstruction? Okay,
they typically have the order of around 15% in terms of their full width at half maximum. We would like to get better than 10%. And ideally, the better the energy resolution, the better our image quality is concerned. And so this is part of the challenge. Yes, they're going in that direction. Are they going there quickly enough? I'm not sure. And so this is why we're starting to look at machine learning as a mechanism to get around this, or hopefully to get around this, this problem, because the algebraic reconstruction techniques are really quite reliant on having, I say we have got images at 10%, but certainly the better images are at the 5% and even less energy resolution.
Okay, great. One more question. Has the CNN PET reconstructions been used with experimental/clinical data, and what is needed before this is done?
Again, an excellent question. No, at the moment it hasn't been. Not in our hands anyway. We've only used Monte Carlo simulations to generate this. One of the steps is, once we've done the variety of testing using our simulated phantoms, would be to start to collect data from clinical systems and to make use of that clinical data to train our networks. But no, at the moment we haven't used clinical data, although there are some investigators elsewhere in the world. They're not looking at scatter particularly. They're looking just at simple reconstruction, PET reconstruction, without focusing on the scatter component specifically, and they have used clinical data and are showing quite credible results. Sounds
good. So I don't think there's any more questions, so I'll take this opportunity to thank you. Thank you for giving a great talk. It's our pleasure to have you, and thank you to everyone for joining us, and hope to see you next time. Thank you.
Thank you very much indeed. Bye-bye.